Hi, we are presenting SpoK, Spark on Kubernetes, which is running big data applications at scale on Kubernetes using Spark. I am Nagaraj Janardhana, Principal Engineer at Intuit on the ML platform.
And I'm Mike Arov. I'm Staff Machine Learning Engineer at Intuit. Thank you.
Intuit's big data infrastructure is in the AWS cloud. S3 is the data lake, EMR Yarn being the primary data processing engine and resource manager. While we had EMR Yarn, we were interested to integrate with the existing Kubernetes infrastructure within the organization. We liked containers over Bootstrap scripts, Kubernetes as resource manager compared to Yarn. We also wanted continuous deployment for our data processing jobs. Let's dig deep into each one of the above areas in the subsequent slides. Services within Intuit are deployed and managed on Kubernetes. The Intuit Kubernetes service allows service developers to manage their service runtime and its deployment. Since Intuit already used Kubernetes, we had an opportunity to have a single resource manager to manage both data processing and service workloads. This would help in management of infrastructure, operations, automation across the organization. This slide shows the Kubernetes infrastructure within Intuit. We have doubled down on Kubernetes since the acquisition of Applytics, the founder of open source Argo project. Containers for data processing jobs are very useful as it helps data workers write their code and deploy it across environments in a standardized and a predictable manner. This, combined with declarative management of Spark jobs, means no more complicated shell scripts to manage. This slide shows containers being deployed declaratively, whereas earlier we used to manage deployments using shell scripts as part of the Bootstraps. This is especially powerful for ML workflows, which have complex configs to manage. Kubernetes is a general purpose scheduler, which was already in use in the organization. Whereas Yarn is a very specific scheduler for managing data processing jobs, which requires expertise and thorough knowledge. Earlier, it had taken us a long time to fine-tune Yarn scheduler to achieve maximum efficiency out of it. It is also quite complicated, as it is hard to find experts to tune, manage, and operate it at scale. This slide shows the scheduler view of an executing Spark job in Yarn and Kubernetes. In Kubernetes, as you can see, Spark drivers and executors are normal pods, and hence you get all the metrics that is available for them. Data processing jobs need to have CI/CD pipelines to have faster build and deploy cycles, as this improves the developer productivity and also improves the quality of production releases. SpoK makes it easier to use any of the industry standard continuous deployment tooling for data processing. ArgoCD is an operator to manage Kubernetes resources. We use ArgoCD for continuous deployment of data processing applications. This was cumbersome earlier due to the complicated shell scripts and multiple set of imperative commands to deploy and monitor status of the jobs. This slide shows a continuous deployment workflow, which builds the Docker image of the data processing application and triggers the orchestration workflow. This is an end-to-end view of a data worker interacting with the processing infrastructure. And this is a Kubernetes native workflow. In the first step, data worker does data exploration using Jupyter notebooks. This have been deployed on Kubernetes as a service. Once the data worker is happy with the results of exploration, he commits the code to Git. Then, primarily using the GitOps deployment, this code is pushed to the different environments using either ArgoCD for continuous deployment or the Argo workflows for orchestrating complicated workflows. There is a high meta store to share metadata of the data stored in the data lake, which is S3. The high meta store is deployed and managed as a service on the Kubernetes cluster. We also have Spark History Server, which is used to monitor the Spark jobs. Spark History Server is also deployed as a part of the Spark operator in the Kubernetes cluster. All this is made possible by the Spark operator, which is deployed to handle Spark jobs across different namespaces. There is one single Spark operator across the cluster. In future, we are looking at deploying it outside the cluster to manage workloads across multiple clusters. Next, we will go through the use cases which have been enabled using this new infrastructure. Mike will walk you through those use cases.
Thank you, Nagaraj. The first example is a very interesting one. It's one of the many batch inference pipeline and machine learning jobs in Intuit. It's remarkable because it powers our mobile application, but in particular, it powers push notifications that is used to drive conversion and increase user base of QuickBooks Mobile. QuickBooks Mobile users can sign up to 45 days free trial, after which they have an option to pay by subscription, or they drop out. We study behavior of all the users who signed up or didn't sign up, analyze the recorded data about their behavior, such as which button they click, which searches they made, which features they tried to use, and which features they didn't try to use. And we make a prediction of whether a current trial user will likely to convert. We also determine 5 actions that we need to recommend to user to increase chances of conversion. Also trained using a XGBoost model, which is deployed and run daily on a batch of all users that joined the trial of QuickBooks Mobile. Previous version of this model ran in Kubernetes for scalability, operations, and service availability, but it used EMR cluster to do feature engineering and ETL. For that purpose, the model Docker, besides the actual XGBoost inference code, had to include special connector libraries and setup to communicate and run jobs on EMR. That required a lot of additional overhead, both in development and maintenance, and had the issues that Nagaraj described when he went over Spark on Kubernetes versus Spark on EMR. Once we moved to this new Kubernetes-based system, things become much easier to use and understand. In fact, we have a fully self-serve mode to launch end-to-end ML model workflow development and deployment that data scientists do almost with no need to include machine learning engineers or data engineers in the loop. The key for this is that pre-processing and post-processing Spark jobs and their drivers and executors are the same Docker pods as the replicated model Dockers and supporting components of the ML platform for notifications and data integrity checking. So you can see Spark ETL job as part of the end-to-end DAG on Argo workflows and easily change in the code, modify. But even more importantly, before you deploy to the Kubernetes, you can run the same ETL jobs on the same Kubernetes cluster in different namespace though, on the regular Python notebook. This setup is much easier than compared configurations for EMR. In order to connect EMR to Jupyter, you need to use Livy server, Spark Magic, and you have to follow non-standard examples of Spark Magic, how to connect to the server. None of this is necessary with Kubernetes. You use the Spark code like any textbook PySpark with no changes. It runs the same Spark on Kubernetes job as on production, and you can even specify the IAM role that will allow to access the same data, the same permissions and privileges. That is the key part to enable self-serve end-to-end ML pipeline. But we can use and have benefit of Spark on Kubernetes, our SpoK, not only for inference, but also for feature engineering. The following example, the features generated were used by multiple models. The reason is because online transaction categories is an important and critical stone of our QuickBooks Online infrastructure. When the user wants to enter their expenses and income in the QuickBooks Online, he has to choose which categories to use. And user have to manage all the categories that are relevant to them. Different users have their own spending categories. They, in addition, the same category that for one user may have different meaning here to another one. In this example, a contractor can see Home Depot expense as expense for materials and supplies. For a tailor, for repair and maintenance. This requires the careful of application of ETL logic. That is, it requires some work on behalf of data analyst and data scientist to carefully filter bad data and polish the good data. But the core functionality is simple and easily distributable on a Spark cluster. We basically join transactions and users table, aggregate, and make a flat record of all users' transactions. An example is shown below. In order to make those features available and reusable by all models, we have to follow the CI/CD processes to constantly update and rerun on a scale. We use ArgoCD tool again from our Argo project division. And we used the Google operator for Spark operator, the same one that we use in all throughout the Spark SpoK ecosystem for launching and controlling jobs. This is an example how deployed transaction categorization features look. As you can see, Argo shows current state, in this case it's green, and how the definitions of the features through Git compared to the current state of the system. And it also monitors the data. So when the data is up to date and to generate those features up to date, it shows the state as green and have those features available in our feature management platform. As useful and great Spark and Kubernetes been, the journey to implementation was not without its challenges. Among others, we had to implement external Hive metastore to connect to our data lake. We also had to create a Spark history server as deployment, which was not available as an open source or ready to use package. We also had to deal with S3A protocol, which is open source implementation of Hadoop to S3 access that emulates functionality of AMR file system. Since we are not running in AMR, we had to use those libraries in our Spark Dockers. But the default build of Spark Docker does not include them. So we had to create our own Spark build pipelines and processes building our own Spark Docker. At the time, the latest Spark version was 2.5, and this caused a number of difficulties, which I'll explain in a moment. Currently, a couple of weeks ago, we had Spark collaboration released Spark 3.0 in June 2018. So any newcomers to Spark on Kubernetes, I would strongly recommend to use Spark 3, which has all the features which we had to custom patch and operate already built in. The two most important issues was dynamic allocation, that was feature not available in Spark until 2.0, and there was a critical Parquet bug that caused exceptions within some of our data files. All of them had to be custom patched in order to make the system usable and useful. But the Spark operator, useful as it is and powerful as it is, has its own share of quirks and problems. The biggest issue that we have to overcome is that it overrides the Spark properties file inside Spark Docker with its own. It needs to do it in order to track dynamic properties like IP of running executors and drivers, but it prevents users from easily make their own Spark configuration available, which we needed. Our solution was rather straightforward. We created a config map of our own, and inside the Docker, we changed the logic to merge the Spark operator's Docker, Spark operator config map with our own and pass it to Spark. Now I'll turn back to Nagaraj, and he'll summarize our learnings and future outlook.
Thanks, Mike, for walking us through the use cases. Here are some of the advantages we have observed of running data processing workloads on SpoK versus EMR YARN. Unified management of clusters across different types of workloads within the organization has been a big win for us. Containers simplified dependency management, and the data processing job also reuse the toolings and support built for containers. Example, Artifactory, CI/CD tools. This has been this is cost effective as OpEx and other resources are shared across. Another big win has been the declarative specification of data processing jobs and the infrastructure associated with it. This makes it easier for data workers to specify and manage their jobs. Next, we will look at the future. In future, we would like to build an ML operator to orchestrate ML workflow and resources through different stages, such as feature engineering, model training, and model deployment. This operator will encapsulate and abstract the nuances of underlying infrastructure and runtime. We hope the ML operator will help declarative specification on what has to be done rather than the how part of it. Also, we are planning to offer Notebook as a managed service for data scientists to explore and visualize the data. Thanks for being with us all this while. Hope you have enjoyed the session. Thank you.
Thank you.